As scientists, we like to believe we know how comets behave. We have watched thousands of them arc around our sun, shedding dust, growing bright, sprouting tails that stretch for millions of kilometers. They obey physics with a kind of cosmic reliability, repeating what their predecessors have done for as long as we have recorded such things. But in 2025, an object swept through the inner solar system that resisted every attempt we made to fit it into the familiar patterns. I will speak of it as an astrophysicist who has spent decades studying small bodies and interstellar debris, but also as someone who felt, perhaps for the first time in many years, the unsettling thrill of mismatched data. The object, known as 3IATLAS, was officially classified as a comet, yet it behaved in ways that forced even the most conservative among us to acknowledge that we were looking at something profoundly unusual. The story began on July 1st, when a faint point was detected on a trajectory that, after the first orbital solutions were computed, clearly did not originate within our own stellar system. Its hyperbolic excess velocity marked it as interstellar, joining the extremely short list inaugurated by Oumuamua in 2017 and expanded by Borisov in 2019. But 3IATLAS immediately distinguished itself by arriving almost perfectly aligned with the ecliptic, the flat disk where planets and most of the debris of our own system lie. Interstellar objects should not care about the shape of our solar system. They are born in distant places with no knowledge of our orbital geometry. Statistical models tell us that the odds of an interstellar visitor dropping into our planetary plane within a few degrees by chance are extremely small. And yet this one did, tracing a retrograde but eerily coplanar path that raised eyebrows before anyone had even examined its coma, composition, or brightness curve. The narrative turned stranger in early October when China's Tianwen-1 probe, long past the end of its primary mission at Mars, was retasked to attempt something no spacecraft had ever done: image an interstellar comet from deep space at unprecedented proximity. The challenge bordered on absurd. The camera was designed for high-resolution imaging of Mars's surface from low orbit, not for tracking a dim, asphalt-dark object 5 or 6 kilometers wide, moving at 58 kilometers per second relative to the Sun and sitting 18 million miles away. Yet engineers managed to retune the instrument's tracking, exposure timing, and thermal behavior so that it could gather a sequence of frames. On November 5th, China released these images to the world. They were fuzzy, grainy, imperfect, but they represented humanity's closest look at an interstellar comet, and at first glance, they showed something anticlimactic: a blurry sphere with a diffuse coma and nothing that resembled the long tail we expected from a body that had just torn past the Sun. This missing tail quickly became one of the most puzzling features. According to NASA's Jet Propulsion Laboratory, the comet underwent measurable non-gravitational acceleration near perihelion, a clear signature of strong outgassing. At roughly 1 astronomical unit, 3IATLAS exhibited radial acceleration on the order of 1.1 times 10 to the minus 6th AU per day squared and transverse acceleration of about 3.7 times 10 to the minus 7th AU per day squared. These numbers are not ambiguous. They imply a loss of at least 13% of the object's total mass during its passage near the Sun. For a 30-billion-ton nucleus, that corresponds to roughly 4 billion tons of ejected material. 4 billion tons should produce a magnificent display of dust, gas, and debris visible in almost any optical instrument. Yet neither Tianwen-1, nor Earth-based observatories in Italy and Spain, nor any other platform saw anything remotely comparable. They all reported a compact coma, a fuzzy sphere, and no distinctive tail structure. The Sun's direction was labeled in each image. The anti-solar direction, where the tail should point, was clear, and it was empty.
At this point, the pattern of anomalies began to expand. The first was the improbable alignment with the ecliptic plane. The second was a sunward jet observed in July and August, material apparently streaming toward the Sun instead of away from it, contradicting what solar radiation pressure should allow. Anti-tail optical illusions are known phenomena, but in this case, geometric and photometric analyses by multiple teams confirmed that the feature was real, not a line-of-sight artifact. No classical comet has ever produced such a jet under such conditions. The third anomaly involved the combination of mass and speed. This object was not just larger, but far larger than either Oumuamua or Borisov, and it traveled faster than both. According to interstellar population models, the probability of detecting an object that is simultaneously this large and this fast is very low, significantly less than 0.1%. The fourth anomaly lay in its encounters. 3IATLAS passed near Mars when orbiters were active, near Venus when ground observations could complement spacecraft data, and near Jupiter in a configuration ideal for long-range imaging. Its perihelion occurred precisely when the Sun blocked Earth-based telescopes, ensuring that the world's largest observatories were blind at the moment when a comet would typically appear brightest. To some, this was coincidence. To others, suspiciously well-timed choreography. The fifth anomaly emerged in the comet's chemistry, an unexpectedly high nickel-to-iron ratio, inverted compared to nearly every comet ever measured, and a nickel-to-cyanide ratio that exceeded known values by orders of magnitude. Nothing in our catalog displays such a composition, and models of comet formation do not predict such a mixture even in exotic stellar nurseries. The sixth anomaly was the astonishing lack of water, with estimates suggesting that only about 4% of its mass was water ice. Instead of being a dirty snowball, 3IATLAS behaved like a rock with a thin sprinkling of volatiles. Yet it was active, showing outgassing despite being far drier than typical nuclei. The seventh anomaly involved polarimetry. The light reflected from its coma featured extreme negative polarization far outside the empirical database of all known comets, including Borisov. No accepted grain models, neither fractal aggregates, nor compact silicates, nor icy shards, could reproduce such a signature without invoking exotically shaped or compositionally unfamiliar particles. The eighth anomaly made many of us uneasy, though cautiously so. The comet's inbound direction overlapped with the uncertainty region associated with the famous 1977 WOW signal. The match was not perfect, about 9 degrees, but closer than one would expect by pure coincidence. The ninth anomaly involved its photometric behavior near perihelion. The object brightened more rapidly than models allowed and appeared unusually blue, as though it were reflecting or emitting light in a spectrum not typical of cometary dust. And then finally came the 10th anomaly, which is ironically less a feature than the glaring absence of one. No tail, despite losing billions of tons of material. Dust tails required dust. Gas tails revealed themselves spectroscopically. For 3IATLAS, neither appeared. If any one of these anomalies stood alone, we would find a conventional explanation. But all 10 appearing simultaneously in one object forces us to ask harder questions. Many scientists, myself included, initially gravitated to the conservative interpretation. A natural interstellar object formed under unusual conditions, representing a statistical outlier in every category. After all, sample size matters. 3 interstellar objects cannot define a distribution. Yet, as new datasets arrived from ground observatories and Tianwen-1 images were reanalyzed repeatedly, the hypothesis space refused to simplify. Every attempt to explain one anomaly seemed to worsen the fit for another. Dust-poor outgassing could explain the missing tail, but not the polarization signature. An unusually dry nucleus could explain the chemistry, but not the sunward jet. And so on. This is where the conversation became delicate. Scientists dislike speculation that leaps too far beyond evidence, but we also dislike ignoring patterns that persist across independent measurements. Some researchers suggested the possibility that the object might have an engineered component, or that its trajectory might have been shaped by non-natural forces long before it entered the solar system. Not necessarily a spacecraft in the science fiction sense, but perhaps a fragment of a larger structure, or debris from an ancient technological process, or a product of stellar engineering we cannot yet imagine. Others cautioned strongly against such ideas, arguing that our ignorance of interstellar object diversity is profound, and that exotic natural processes surely exist in the galaxy. Both sides agreed on one thing. 3IATLAS did not behave like any comet in our experience. By November and December, the window for close observation was closing. The object was moving outward at over 200,000 kilometers per hour and would soon be too faint for detailed study. The data we gathered, images, spectra, astrometric records, polarization curves, would have to suffice for decades of analysis. Tianwen-1 provided our best close-range view, ground-based observatories captured the last of the object's brightness curve, and the final astrometric points refined the orbit before the visitor slipped permanently back into the deep dark between stars. Estimates indicate that by January 2026, it would fully exit the heliosphere, beginning a new chapter of its interstellar journey. This object has left us with more questions than answers, and perhaps that is its most meaningful contribution. It reminds us that the early era of interstellar object astronomy is not a comfortable one. We began with nothing but theory. Then, Oumuamua arrived as a shape-shifting enigma that accelerated without a visible exhaust. Then came Borisov, far more conventional, yet chemically odd. And now 3IATLAS, by far the most massive, most puzzling, and most dramatically irregular of the three. 3 objects, 3 very different stories, and almost no overlapping behavior between them. If this is the beginning of our sample set, what will object number 10 look like? Object number 50? The galaxy could be filled with bodies displaying physical behaviors beyond anything seen in our solar system. Future observatories, especially the Vera C. Rubin Observatory, will likely detect many more interstellar objects. Some may be small and dim, others may be larger and stranger than 3IATLAS. With improved detection pipelines and rapid response missions, we will be able to intercept them or observe them with far better fidelity. We will have polarization data from the moment they brighten, spectroscopy from the moment they begin to outgas, and imaging teams coordinated across Earth, Mars, and perhaps lunar orbit. Each visitor from another star will expand our understanding of what distant systems can produce.
And at some point, maybe in our lifetimes, maybe centuries from now, we may encounter an interstellar object whose anomalies are not merely numerous, but unmistakable, whose properties cannot be stretched to fit natural explanations. If such a day comes, our readiness to recognize it will depend on our ability to treat objects like 3IATLAS with intellectual honesty. Not to sensationalize them, not to reject exotic hypotheses out of hand, but to build analytical tools that can discriminate between the bizarre and the artificial, between the unlikely and the impossible. For now, 3IATLAS remains an unsolved puzzle. It behaved like a comet, but without a tail. It lost mass violently, but left no debris. It aligned with our ecliptic as though following a script, produced a jet in the wrong direction, brightened in the wrong color, polarized light in the wrong way,
and departed the system, leaving behind data that will occupy researchers for decades. It may turn out to be entirely natural. It may turn out to be profoundly significant. But whatever it is, it has already made its mark on astrophysics. It taught us that our assumptions are fragile, our models provisional, and our confidence in what comets ought to do is more limited than we like to admit. Somewhere beyond the orbit of Mars, the object is already fading into the dark, carrying with it the chemical imprint of its birthplace, the scars of millions of years spent wandering the interstellar cold, and the final traces of the solar heat that stripped away part of its mass. It will not return. No generation after ours will see it again. But the data remain, etched into our archives, waiting for sharper minds and newer models. And out there, in the vast gulf between stars, another object is already inbound. We do not yet know its name, its trajectory, or its nature. But we will. And when it comes, we will measure it with sharper eyes, wiser caution, and a renewed willingness to confront the unknown.